Welcome back, Year 11 Physics. This is the third of 5 topics for Year 11 Physics Double Science. The previous 2 topics were distance, speed and acceleration, forces, and this is the third topic on work and energy. This is Moodle, of course, where everything is brought together in terms of the video and quizzes and so on. I just wanted to show you that so you know where this fits in the rest of the course. So please start by just filling in the front of the booklet, name, form, set and teacher. As always, on the first page of the booklet you have the equations, both foundation and higher tier, that will be given to you in your exam with the multipliers, SI standard, international multipliers for foundation and for higher tier. Page 2, as always, is where you'll have the feedback, close the gap marking, and turn then please to page 3 and just write down the title, Lesson 1 work done, and the date on the top. This is the specification, and in this lesson we're going to learn about what is work done and the fact that work is a measure of energy transfer. We're going to use this equation, W equals F times T, which is work equals force times distance. There's some more information there that you can read through. And also the fact that when a force acts on a moving body, energy is transferred although the total amount of energy remains constant. That's the principle of conservation of energy. The total amount of energy remains constant. There's a chapter summary here that will be useful for revision. I won't go through that now. So we're going to start to learn this topic of work done and energy by considering a rugby match. You may well have watched this yourselves about 5 years ago now, and it's a match Wales against England, and you can see Alan Wyn-Jones, captain of Wales, lifted up, here he is, by 2 of his fellow forwards, and he's 1.98 meters tall and he weighs 118 kilograms. The players lift him effectively, raise him through 1.5 meters. Now these 2 numbers here are the important numbers, and doing so have to generate an upward force between them that is greater than his weight. Now what you have to be able to do is work out how much energy is transferred from these 2 players here. It looks like Bradley Davis to me. Ooh, and possibly, I can't work out that one, possibly Dan Lydiate, difficult to tell. Or, yeah. How much energy it takes to lift Alan Wyn-Jones that far off the ground. And the good news, of course, is Wales won the game. We'll be using an equation, work equals force times distance, and the force needed to pick a player off the ground will be equal to his weight. Now in order to work out his weight, what we need to do is use this equation. Now straight away there's a potential for confusion because we're using W here for weight and we're using W here for work done. So I wanted to point that out straight away. So what I'm going to do to avoid that confusion is just zoom in and write out weight in full, because the weight of Alan Wynne Jones is going to equal the force needed to pick him off the ground. So we'll go back, that's 118 kilograms is his mass. And we'll take G as 10, so his weight therefore would be 1,180 newtons. To work out the work done, or energy transferred in picking him off the ground, or lifting him, I should say, off the ground, we multiply the force required by the distance he was lifted, and that's 1.5 meters. 1.5 meters. So you just get your calculator and work out the answer. So we multiply the force by the distance, and that's the energy transferred. Notice the unit for energy is joules. Turn over to page 4. First thing you need to do there is just write down the definition for work done. It's actually in the chapter summary at the top here. I've written it down. Work is done when energy is transferred from one form to another. The work done is a measure of the energy that's transformed. Notice these words sometimes are interchangeable. Transferred and transformed. It just means changing from one to another. Energy can be changed or transformed in many different ways, but the energy itself cannot be created or destroyed. Those are the two key words: cannot be created or destroyed. There's a finite amount of energy in the universe, so we can't create anymore, we can't get rid of it. What we're simply doing is transferring from one form to another. What we're asked to do here is to complete the energy changes involved in a rugby line-out. So first of all, it asks, right, what is the stored energy inside the players? And that's chemical energy. So you'd write down on that first line, chemical. And chemical energy, remember, is what you have in food. That's changed to, or transformed into, kinetic energy as the muscles start to lift Alan Wynne Jones upwards. At the highest point above the ground, the player has a type of potential or stored energy that is called gravitational potential energy. We've learned this before, so this is just a recap. So when you pick up something off the ground, so that's the ground, and you raise something upwards, vertically upwards, you're increasing the amount of gravitational potential energy that it's got. Okay. As work or work done involves measuring a transfer of energy, we measure the work carried out in joules. Joules, remember, is the unit of energy. Remember that 5,000 joules is the same as 5 times 1,000 joules, which is the same as 5 kilojoules. In this orange box is a reminder, we've used the weight equation before. Add units to the variables below. Pause the video, and I'd want you now to write in what you think are the correct units. What you should have written in, weight is a force measured in newtons, mass, kilograms, and gravitational field strength, newtons per kilogram. That's the hardest one to remember. Also remember that weight is a force, and to keep an object up, like holding a cup of tea, we would have to use a lift force equal to the cup's weight. So if I did a quick drawing of a cup, you hold the cup, so the force that your hand is applying is effectively that way. So we call that the lift force. There's other forces your hands are applying. Your hands are acting on the sides of the cup as well, but they balance each other out. So the weight of the cup acting down equals the lift force acting up. Let's look at this equation underneath. This is the equation that, as always, you're given in the exam, but you have to be able to use. I'm going to do question 1 and 2 as an example, and I'll be asking you to do some questions yourself later on. This is almost the same as the example I did above. The only difference is this time they haven't lifted him so high. It's 1.4 meters. G remains the same, his mass stays the same. So to calculate his weight force, weight, and I'm going to write it out full so we don't confuse it with work done. It's mass times G. That's exactly the same as the example further up. To get the 3 marks there, remember I've taught you plenty of times before, ENO, so equation, numbers, answer, and units. Calculate the work done by both lifting players, so the combined force that these players are applying to Alan Wynne-Jones. So work done is force times distance. The key here, of course, is to remember that the force is equal to Alan Wynne-Jones's weight acting down, which is 1,180. The distance lifted this time is 1.4. So all we do now is put in those numbers in the calculator, and this time, as you'd expect, because he isn't lifted as high, he hasn't gained as much gravitational potential energy. Alan Wynne-Jones, this time, the amount of energy being transferred to him is 1652 joules. I'll explain why Mr. Ruddy's included this wrapper in a moment. You should have found out that the total work done by the rugby players is 1652 joules. Pause the video and write that in here in terms of kilojoules. What you should have written down is that it's 1.652 kilojoules. Use the data above, work out how many times Alan Wynne-Jones could be lifted using the energy that is stored in one chocolate bar. Let's look at the chocolate bar. If we really zoom in, it says per bar there's 995 kilojoules of energy. 995. I'll write that down before I forget. 995 kilojoules. That's the energy per bar. Chocolate bar. Now this is where you need to apply your numerical reasoning. Two numbers we need to think of. Firstly, how much energy is needed to lift Alan Wynne Jones, and how much energy do you get from one bar. And the key here is for you to realize that the number of lifts is calculated by dividing energy per bar, or in one bar, divided by energy needed for one lift. Energy used. Just added in the energy per bar, 995 kilojoules, and the energy used per lift, 1.652 kilojoules. So the number of lifts, let's just check that again, to the nearest lift, 612. So what that's saying is you get enough energy from that chocolate bar to lift Alan Wynne Jones 612 times. Underneath it says, why in practice would that number of lifts not reach that number, assuming the lifting players do not become tired? In other words, what is asking, why in reality can't you lift Alan Wynne Jones 612 times from the energy of that chocolate bar? It's to do with wasted energy. Not all the chemical energy in the chocolate will be converted into kinetic energy in the muscles. A lot will get wasted as heat. A little more on that later. But I'll allow you now to just pause the video and write that down in your own words. Rewind the video if needed. Okay, continuing with the rugby theme. It says, during a scrum, 8 players each push with a mean force of 600 newtons. Moving the scrum 2.5 meters. What's the total force exerted by all 8 players? So I'll go through this one with you. Total force. If you're going to write this out properly in true numerical reasoning style, you will come up with your own equation. Total force is force per player multiplied by number of players. And if we check at the top, it says each pushes with a mean force of 600 newtons. So 600 for force per player, and there's 8 players in a pack. So you multiply 600 by 8. $4,800. And force is measured in newtons. To calculate the total work done, you multiply the force by the distance. So all we need to do here is to use that equation. Work done is force times distance, and the distance tells us up above is 2.5 meters. That's how far the scrum is pushed. And remember that energy is measured in joules. We could convert that to kilojoules, 12 kilojoules. Right, question 2 is a self-assessed question. That's where I'd like you to do the question first. There, pause the video. So pause the video now and do the question. When you've done the question, press play. What I'd like you to do now then is compare your answer to the one I'm going to write down now and self-assess with the red pen. So it's asking, in a head-on driving tackle, a rugby player does that much work, 1,650 joules, drives the opponent back by 3 meters. Calculate the force of the tackler. Yes, excellent technique in that tackle. So the force being applied here, we're saying is 1,650 joules, 1,650. Looks like it's Northampton against possibly a French side in the Heineken Cup or European Cup. Anyway, let's do the calculation. Force of the tackler. Well, what do we know? We know work done. We also know distance, and we've been asked to work out force. Therefore, we can use the equation W equals F times D, and we can rearrange that equation. And if you wanted to, you can use this triangle method, or you can use a bit of algebra, which effectively means you would divide both sides by D. Okay, so if I divided both sides by D, that would leave us with F equals W over D, or you just use the triangle method here, and you could rearrange that way as well. So whichever way you do it, F equals W over D. Force is work done over distance. Work done, 1,650 divided by the distance, which is 3. I think that's 550. Let's check that. So we got 1,650 divided by 3, 550 newtons. Self-assess. Question 3 is one for you to do. Read, think, and answer. Efficiency is a topic we've done in year 10. You learned how to do Sankey diagrams then, so I'm not going to go in too much detail, but what it's asking you to do is turn this information into a Sankey diagram. As was explained above, not all the chemical energy in food is transferred into useful kinetic energy. In fact, the majority of it is wasted as heat energy, and that's why when you exercise you often sweat, because of the heat that your muscles generate. So just remember to use the correct scale. Each small square is 2 joules. So you're just representing the transfer of energy, and because only 25 joules of energy is transferred into kinetic energy out of the 100, we say then that the efficiency is 25%. Make sure you use a ruler, make sure you label the different transfers of energy are included with the different forms of energy. Okay, that's that. Moving on now to page 9. You may recognise the rugby player, Johnny Wilkinson, training. Question is to calculate the work done on the sled. If you read the paragraph above, it says that players typically pull the sled with a force of 450 newtons through 20 meters. This is a self-assessed question. So you need to pause the video in a moment. You answer the question, then you press play and compare your answer to the one I write down and mark it with a red pen, tick it if it's right, and make any corrections in red if needed. So, first of all then, what needs to be done is work out the work done, which is question 1. Remember, equation number, answer units, E, no. The force, which is taken from the top, is 450 times 20. I think that's 9,000. 450 times 20, 9,000 joules. And question 2, if the player's muscles are only 25% efficient, calculate the work done by the player's muscles. Now you could answer the question using this equation we used in year 10, or more simply, 25% efficient means that useful output energy, which is 9,000 joules, is 25% of the energy supplied. So the energy supplied, or the total work done by the player's muscles, work done by muscles, is going to be 4 times 9,000, because 9,000 is 25%, and if you want to work out 100%, you multiply 4 by 9,000. 4 nines, 36, so 36,000 joules, or 36 kilojoules. You don't necessarily need to use this equation, but you can if it helps. And final activity for this lesson is based on this practical, and I've just put a line through what you don't need to do, and I'll cross up the risk assessment part here as well. Now, if you're doing a risk assessment, what's the hazard? Well, let's look at what you're doing first of all. Stepping up onto a step, and in 30 seconds working out the work done. So the risk, the hazard there will be an unstable step, the risk will be falling off the step, and the control measure you'd put in place would be to check the step is balanced and can take the person's weight. So I won't ask you to do that, but what I would like you to do is basically A, B and C underneath, which is calculate the weight force of moving the weight using that equation highlighted, then the work done using this equation, and the total work done by the number of repeats you complete in 30 seconds. So we need to know a few things. We need to know the mass in order to work out the weight force, and I've done that first one here for you. The distance moved is 0.4 meters, so that's the height of the step. That's this height here, 0.4 meters or 40 centimeters, and that will allow you to calculate B, and to work at the total work done you need the number of steps in 20 seconds. That's here. Don't forget to complete the plenary assessment. That's the end of lesson 1, page 10. See you next time. Bye.